5.6 substitution rule. And what we're going to do in this section, this is part one, we want to make sure we can always take the derivative of an antiderivative to check our work. Because right now we've only been doing a little bit of constants where we do the anti-chain rule kind of situation. But what if it's not just a coefficient of a number that's our anti-chain rule? So we need something else. And this is where we come up with substitution. And it says here for the theorem 5.9, we're going to let u equal g of x, where its derivative is continuous on an interval, and the function f is continuous on the corresponding range of g. So what we're saying here down here, if we have something that looks like x times, how about, I'm sorry, let's do 2x, and it was something like x squared plus 1 dx. And right now we look like we have a multiplication thing going on. What do we do here? This is a little goofy. What if really one of these functions we'll call f of x and the other one is g of x, where it's then really the derivative of this inside function here. And that's where we have this chain rule going on. But in order to make this simpler, what if I was really saying, well, if I could substitute in u for it, what if I just got u du, and I can easily take the derivative of that. And that's what we're saying here in this substitution rule. So there's procedures we want to do with it. We're going to be given an indefinite integral involving a composite function. Composite function. It's one function inside of another, f of g of x. And we're going to identify the inner function. We'll name it u. And then we can take the derivative of it as it appears in the integrand. And that's an important part. It has to look the same that's already in the integrand. So we're going to substitute u, we're going to take the derivative of it, and we're going to solve for du so that we can get the derivative of g dx and have that match what's in the integral. So then we're going to evaluate the new indefinite integral with respect to u, and then we're going to go back and re-substitute it in. Disclaimer says not all integrals yield to the substitution rule. Sometimes it does not work well in our favor. So I'm going to go ahead and start doing some examples. We have number 9, and we're given this function of x plus 1 to the 12th power. And we're going to go ahead and try to set up an indefinite integral. Oops. And from here, we know we're going to use, this is our function, and then dx. But right now, this is kind of a messy situation, so we're going to go ahead, this is easy. We're going to go ahead and use u, we're going to say let u equal, and we're going to do the inside of that parentheses. And we're going to go ahead and take the derivative of this, du dx, and the derivative should be 1. I am then going to multiply both sides by my dx, and I get du equals 1 dx. Notice now, I need to substitute not only the variable, but the dx. So I'm going to use du to replace dx. And we said u was going to be this x plus 1. So I'm going to go ahead and substitute u for the parentheses. And then I still have the outside function of 12 power. So I'm going to go ahead. This is now becoming much easier to take the integration of. And we see that it should be add one exponent to the exponent, divide by the new exponent, plus c. But the last step is to go back and resubstitute for the u. And I see that it should be the x plus 1 to the 13th power over 13 plus c is now my answer. This one may not seem as bad, but technically it was a composite function. Remember, this was the inside function, the power was the outside function. So let's go ahead and try another example. We're going to do number 15. And I'm given sine cubed of x cosine x dx. Well, this one is definitely many different functions. I have sine is an inside function and cubed is the outside function, and then it's being multiplied. So I'm going to rewrite this so maybe it's a little easier to see. So that I can say, okay, sine x is my inside function, the power function of 3 is the outside function, and notice it's being multiplied by the derivative of the inside, that chain rule dx. So in order to make this easier to find the antiderivative of it, I'm going to let u equal the inside function sine x. I'm going to take the derivative of both sides. And I see that this cosine x is definitely in part of my integrand, so I'm getting closer to be able to substitute. I'm just going to go ahead and multiply this both sides by the dx. And now I have this to replace here, so I can replace that with du, and I'm going to replace sine x with u. So when I go ahead and write my integral again, it's now going to be u cubed, and I'm replacing the cosine dx with du. Much easier to take the antiderivative now, and I see that it should be equal to u to the fourth over 4 plus c. Last step will be to resubstitute in for u, and I see I have sine to the fourth power of x and over 4 plus c. So let's go ahead and do another one. We're going to do number 19. 19 gives us this integral. And now this becomes a little bit of a trickier one because you're thinking, what do I want to try to substitute here? I see that maybe my chain rule is the 2x squared, but when I look at what's inside is my g function inside the f function, I don't know. I can try to do that, but it kind of may not end up being the same. So I'm going to do make things a little bit easier to see. I'm going to make this all in the numerator. I'm going to bring up this square root, and I'm going to put it in exponential form. And now from here, I'm going to go ahead and say, let u be this inside messy function, g of x. And then I'm going to take the derivative of it. All right, so now I see I have this x squared in my radicand currently, but I have a negative 12. And over here to the left, I have 2x squared. So I want to be able to replace the 2x squared. So I'm going to have to make over here, when I multiply both sides by my dx, I want to make sure this looks like the 2. So I'm going to go ahead and multiply both sides by the dx, but I'm going to divide both sides by negative 6 so that I now have this. I have du over negative 6 is equal to 2x squared dx. And that way now I can replace this with this. I'm going to go ahead and replace the inside function g of x with my u. So currently I should have u to the negative 1/2, and then I'm going to multiply it by the du divided by negative 6. All right. I got everything inside the original blue function or integral. I'm going to go ahead, got everything substituted, but now I want to deal with this -6 in the denominator here. Remember, this is just now a coefficient, so what I can do, coefficients can be pulled out of the integral as a multiple. And now that that -1/6 is out of the way, I can definitely go ahead and take the antiderivative. So taking the antiderivative in this case would be u. I'm going to add 1 to the exponent, divide by the new exponent, which is 1/2. Simplifying it by taking the reciprocal, I get 2, and then it's plus c. I'm just going to go ahead. I'm going to simplify this first. I have -1/3 u to the 1/2 plus c, and now last step will be my resubstitution in, and I should get -1/3 parentheses 1 minus the 4x cubed raised to the 1/2 plus c. If I really want to neaten this up, maybe in its correct form, I'm going to go ahead and put my radical back in plus c. Either form is correct, but in math we may like to see the radical in instead of a rational exponent. One more problem. I'm going to go ahead and do number 29. Given this integral, in this case, my first instinct was to go ahead and let u be 1 plus the 4x squared. The only problem with that, if I take the derivative of it, it would be 8x. But there is no 8x or any x extra in my integrand. So that's not going to work. This one's a little bit more tricky because of that. When you can't just pick this in order to go ahead. But if there's no extra variable in there, we can't do that. So I'm going to go ahead and manipulate this one a little bit and make it look like this. And in this case, I can see what it looks like a little bit better, and taking the derivative of 2x gives me only 2. I can deal with a coefficient and not an extra variable. So in this case, I'm going to go ahead and let u be 2x. So when I go ahead, I'm going to take the derivative of this, and I see it's 2. Solving for du, I get 2 dx. Like I said though, but we don't have a 2 in there. We can just divide both sides by 2, and we now have du over 2 is equal to dx. I can go ahead now and do that substitution and my u substitution. So I'm going to go ahead and have in here my integral du. I'm going to split this apart first. Let's do 1 over 1 plus u squared times du divided by 2. That 1/2 really is what I'm going to factor out of my integrand as a coefficient. And I now have 1 over 1 plus u squared du. This now is becoming much easier to see what the antiderivative of this would be. It would be 1/2 tangent inverse of u plus c. Last step would be going ahead and plugging in resubstitution u with 2x. So I have 1/2 tangent inverse of 2x plus c. And remember, we can always take the derivative of this, and I should get back to the original integrand, and it does.